Yesterday we did an overview of the observations of binaries, and way is how we can extract parameters of binaries, and I ran through the single evolution. So we can now start working on binaries, and just to remind you, most stars are in binaries. The single evolution is not enough. It's not sufficient to explain the rich phenomenology that we see in the sky. And there are lots of mechanisms that make star interact. So there is quite a lot of possibilities of mass exchanges between stars, and you can have the mass loss from the system. So not only the stars can exchange mass, they can shed mass away and get rid of it from the system. And I'm just mentioning this very important part, which is globular clusters. So in globular clusters you have even much richer phenomenology, because the globular clusters are very dense stellar regions, and in the dense stellar regions you have collisions between binaries and single stars, or double binaries, and in such collisions you can exchange partners. So you can first have some mass interaction, mass shedding in one binary, then exchange partners, have another mass transfer. You can eject some binaries out of the globular cluster. So here the possibilities are endless. So it's a next level of complication that is important to understand what we see in the skies. So now I'm going to go to the binary stars and start working on binary stars. So what I'll be talking is essentially things that are either late high school or undergraduate physics. Everything will be most things will be, except one, non-relativistic classical mechanics that you probably know by heart. So this is like to remember the basic formula that are important for the binary motion, for this system of two bodies moving around one another. You probably have solved it a number of times in physics or introduction to astronomy or whatever classes. So the problem of two bodies in a central potential can be reduced to a problem of a mass with the reduced mass moving around the second mass, the sum of masses. So you can write the energy of the system like this, where mu is the reduced mass, which is mu m1 m2 over the sum of masses. And another notation that I will use is this. The second, this is one thing. The second thing, which will be important, is the angular momentum, and we usually write the angular momentum in this way. However, when we have the orbital motion, it's good to express it in the for example, in such a way where J is mu square root of GMA. And in most of what I'll be talking about, I will assume that the motion is on a circular orbit, not to make things too much complicated, but of course one can generalize all the formula and include ellipticity, but I'll talk why in many cases the ellipticity is not really important for all of the interactions that I will mention. So this is m1 m2 over m to 1/2 square root over GA. Yeah. So we can cancel out this this m, and this is an important formula that we will use later. So just to, for completeness, if you want to know exactly how the motion on an elliptical orbit proceeds, it's good to know the formula for the trajectory as a function of such parameters as energy and the angular momentum. So the radius of the orbit as a function of phase is given by such a formula, where this is the ellipticity, and this is so this is the ellipticity. That's a parameter p, and it's just for completeness. Another important formula that is going to be just floating around all the time is the Kepler's law, which everybody probably knows by heart. So here we have it, and we'll be juggling around this simple formula many times, which is m over a to the third is equal to omega squared, where omega is 2 pi over p. So this is a short introduction to the mechanics of what is happening in orbits. So now that we are over with this, if we have a system like two bodies, or any system of rotating bodies with some angular velocity, the question is, and we have some energy dissipation mechanism, the question is, what would be the state that the system wants to relax to? And I'm going to convince you that I'm going to try to convince you that the configuration of the lowest energy for such a system is the rigid rotation. So there is this theorem that you have a given mass distribution, then the lowest energy state corresponds to the rigid rotation, and let me just try to prove it. So suppose that we define a system that has some distribution of mass, then its moment of inertia will be equal to the integral of r squared dm. The angular momentum is the integral of r v phi dm, and the energy, the kinetic energy, is 1/2 v dm. Yep. So one thing that I will need in proving this point is this identity, which just says that the scalar product of two vectors squared is less than the product of two vectors. And I think this is basic thing that doesn't require a proof in such an audience. So the way we go here is as follows. I'll put it on the blackboard. Let's calculate this first line, I times y phi squared dm. Square the integral of r squared dm is v EM. And now we use my theorem that this must be larger than equal than R dm squared. So now the kinetic energy that we have here, it's T, and this is equal to squared, yeah? So we have the following equality, that's V squared dm is greater than equal to J squared over I. So now the kinetic energy is equal to 1/2 V squared dm, and this is certainly larger or equal than 1/2 over V phi squared dm, because we drop all the other components of the velocity. So we assume here this becomes equality when all the bodies move around one axis. And now we have this. So this is greater than equal than 1/2 J squared over I. And this will be this will be equal for a rigid rotation, because for the case of rigid rotation, we'll have the following. We can write that V phi here, if V phi is equal to omega times, then what we have here is this will be equal to R squared dm, R squared dm times omega squared. And this is equal to moment of inertia squared omega squared, yeah? So in this case we have this will be V phi squared dm is equal to I omega squared, yeah? And here this will be equal to I squared omega squared, yeah? So they will have 1/2, so in this case this would be 1/2 I omega squared, which corresponds to the kinetic energy in the case of the rigid rotation. So this is the theorem, and what are the consequences? So if we have a binary system and we want to make it look like it's rotating rigidly, so we have some energy dissipation, we can get out energy out of the system. So if we treat the stars as point masses, the only thing that makes the system differ from rigid rotation is the fact that there is ellipticity. So if we have energy dissipation, the system will tend to be circular. Okay? This will be the lowest energy state. And the second thing is that if the stars are not point-like, but they have some extent, and we have some energy dissipation mechanism, then the stars will want to rotate synchronously with the orbital motion. They will be tidally locked, yeah? Like the moon is tidally locked to Earth, or Mercury is tidally locked to the sun, so they will just face one another and rotate with same angular velocity as if the whole system was a rigid body. So this is one argument that once we have some energy dissipation in the system, then the systems will tend to become circular and will evolve towards tidally locking and towards the rigid rotation. The point is that we have to have these mechanisms that make them tidally locked, and the tidal forces depend very strongly on the distance. So the time scales, I will not put the formula here for synchronization of the orbit, are proportional to the orbital size in the 6th power. For the circularization of the orbit, it's orbital size in the 8th power, which means that systems that are on very tight orbits will circularize, will become synchronized very quickly, but most of the systems will have to wait for their radii to expand and for the mechanisms of energy dissipation to become efficient, to circularize and to become synchronized.
So what is the dominant dissipation mechanism at this separation?
Well, at which separations? for the stars at the on the main sequence, when we start the evolution, the main energy dissipation mechanism will be tidal deformation and tidal interactions. Once the stars start to evolve and become large enough to fill their Roche lobes, the dissipation mechanisms are, the tides are becoming very important, and there is also hydrodynamical friction because the stars are not, for example, a rotating star that fills the Roche lobe is not spherical anymore. So there is lots of friction when you try to rotate a star within its Roche lobe. So then the energy dissipation mechanisms are becoming much more important. But this is mainly hydrodynamical friction within the star, and because of tides or other mechanisms that start to play a role. Okay, so this is to argue that systems, when they start to interact, will tend to be circular and may become synchronized. Now let me start putting in together the different evolutionary blocks that I mentioned at the beginning of the last lecture. And the first mechanism that, if you have two stars, apart from the evolution of the stars, you have to calculate the evolution of the orbit when the stars do something. The first things that every star does is every star, including the sun, sheds some mass in the wind. Yeah? So we have these two stars, and they are losing mass in the wind. And this mass, depending on the velocity of the wind, may stay in the system or may leave the system, or depending on magnetic fields, it can even do some more nasty things. But let's start from a very simple model. Suppose that we have the two stars, and they have winds that have velocities much higher than the orbital velocity. So the matter leaves the stars and carries away some angular momentum, that is the specific angular momentum of each star on the orbit. So then the question is, what happens with the orbit when the system starts losing mass like that. So we have circular orbits, and we have the following. Oops. We have two stars. Yeah, that's A1, A2, M1, M2, and they have some angular velocity omega. They are rotating around one another, and the amount of angular momentum that leaves the system is omega A1 squared d m1 plus omega A2 squared d m2. Yeah? Now, A1 plus A2 is equal to A, and the radii of the orbits around the center of mass are as follows. A1 is A times m2 over m, where m is the sum of masses, and A2 is A times m1 over m. So this amount of angular momentum that leaves the system is omega A squared, and now we have A1 squared, so it's m2 squared over m squared d m1 plus omega A squared m1 squared over m squared d m2. And now we know that, did I write it anywhere? I didn't write it. Here, another way of writing the angular momentum would be, it's mu A squared omega. Did I put this omega? Okay. So A squared omega is over mu. So we have J over mu times m2 over m squared dm1 plus m2 squared m1 squared over m squared dm2. What we can do, this is J, J and mu is m1, m2 over m times m2 squared over m squared dm1 plus, again, m over 1 m2 m1 squared over m dm2. Okay? So this will be equal J times, and we have m2 over m dm1 over m1. Yeah. m2 over m Okay, so now we have the dj is equal to j times this, so dj over j is what is in this parenthesis, and dj over j is the logarithmic derivative of j. So from we haven't now used anything, any information about the motion in the Keplerian orbit, but use this formula here, and we can write that dj over j is equal to dm1 over m1 plus dm2 over m2 minus 1/2 dm over m plus 1/2 dA over A. Here we can obtain it by taking a log of this equation and then differentiating it. Yeah? And this formula is something that I was put in a red box, because this is something that will be coming back and back many times when considering the evolution of the orbit under the influence of various factors. So we can equate this, the evolution of angular momentum, the constraints on the angular momentum in the orbital motion, with the rate that the angular momentum is lost from the system. And from this, we'll obtain something like, okay, I can get rid of this already, I think. So we'll have m2 over m dm1 over m1, m1 over m dm2 over m2 is equal to d1 plus d minus 1/2 d m plus 1/2 d A over A. Yeah? Okay, so let me put things on this side. So we have dm1 over m1 times m2 over m minus 1 plus dm2 over m2 m1 over m minus 1 plus 1/2 dm over m equals to 1/2 dA over A. We can now dm1 over m1 times m2 minus m1 minus m2 over m plus dm2 over m2 m1 minus m1 minus m2 over m plus 1/2 dm over m equals to 1/2 dA over A. And then we have, this is dm1 over m minus dm2 over m plus 1/2 dm over m equals to 1/2 dA over A. And I'm getting to the finish of this, because this is dm over m, so we can add this to this 3 and obtain minus 1/2 dm over m, which will say that minus dm over m is equal to dA over A, which can be easily integrated to obtain a simple formula A times m is equal to constants. Yeah? So if we lose the mass in the wind, then the orbit will shrink, and the amount of shrinkage of the orbit will be inversely proportional to the total mass lost from the system. Now, in order to do a little bit of juggling, what does it imply for the period? How will the period of a binary change when we lose the mass in the wind? We have to use the Kepler's law, or we can rewrite the Kepler's law in the following ways. We can write that m p squared over a to the third is constants, yeah? Because we have m over a to the third is 2 pi over p. So m p squared over a to the third is constant, and if we know a times m is constant, then from this we have m to the fourth p squared is constant, so m squared p is constant. Yeah? So either this or that, this is equivalent. So the orbit will shrink, and its orbital period will become shorter and shorter, and this is the way it's going to happen. But what we have assumed here that has to be taken into account that the mass loss rate is at high velocity, so the mass disappears from the system right away, but it disappears slowly. It disappears on a time scale much longer than the orbital time scale. So we lose the mass from the system slowly, and the mass loss is immediate, but at a very slow and slow rate. So now that we have this, so with the stars can lose mass, their orbit will shrink slowly, and depending on how quick the mass loss is from the system, this will be, this may lead to contact, but I've been talking about the contact and Roche lobe. So what is this Roche lobe, and how do we define the contact of the stars? So everybody probably has heard the notion of the Roche lobe, and how do we really define it, and what we take into account and what we neglect when defining the Roche potential. So what is the potential that a test particle feels when it is in the neighborhood of a binary? So this is a formula that was given by Edward Albert Roche in the mid-19th century. So we, of course, have the contribution of the potential of one body, the contribution of the potential of a second body, and there's this third part of the potential, which corresponds to the fact that we think of a particle that is co-rotating with the system. Yeah? So this particle feels the centrifugal force due to the rotation, co-rotation in this system. So what is neglected here? Coriolis force, yes. So we assume that this particle is not having any significant velocity in the system. Now, if you have, so the Coriolis forces is neglected, and we have this potential, and here you can see how the the potential looks like. So it's not going to 0 at infinity, it falls down to minus infinity at infinity. So this falls down very much here. Why? Because we have the assumption of corrotation, and if something is corrotating, then it is feeling this force that tries to throw it away if it continues to corrotate with the system at large distances. So this is shown here in the falling of this potential. And then we have these two potential wells and a little saddle point between them. And the Roche lobe volume is defined as follows. We have the value of the potential here on the saddle. So this is the point where between the stars where which is the unstable equilibrium point, L1, and we draw the equipotential lines with this value of the potential, and then we calculate the volume of the region that is under this potential spheres, these potential shapes, and we want to give a characteristic size to this potential, to this value. So we define that the Roche lobe radius is the radius of the sphere with the same volume as the Roche lobe region, which of course is not spherical. Yeah? So now a question. If we have this type of the potential, what does the Roche lobe radius depend on? It is a function of what? If you were to reduce the problems, what are the variables that define the Roche lobe radius? So maybe I'll write down this potential and try to come up with an answer while you digest this. It will depend on two masses, but will depend on the masses, or will there be some function of the masses that is ratio of the masses? Yeah, but can you see how does it come from this?
Combination of masses.
Yeah, omega b is given by this. Kepler's law applies. It's a universal thing in this.
Potential surface, I think we cancel out any kind of explicit mass. I mean, you can write that.
Yeah, it will. It's not that easy. So let me just try to show it to you. F1 is equal to minus g m1 over square root over x minus a1 plus squared. So we have q equal m1 over m2, and m1 plus m2 is equal to m. Then I have this here. Then m1 is q times m2, so m2 is equal to m divided by 1 over q, and m1 is equal to q by 1 plus q times n. Okay? We can express m1 and m2 in terms of the total mass and the mass ratio. Now, A1 and A2 can also be expressed like that, because A1 is equal to A times 1 over M1 plus M2 over M2, which is A over 1 plus 2, and A2 is okay, A over M1 plus M2 over M1, so it's A over 1 plus 1 over Q, so Q. Yeah? So let's express all the that's minus GM, M1 is Q1 plus Q, and we can now introduce all the distances as x over a. Everything will be expressed in the units of, so this will be GM over a, x minus a1 is 1 over 1 plus q plus y squared plus z squared. Yeah. So this potential can be expressed as minus gm over a, and there's a function of and q. Yeah. So the Roche lobe potential, that's q over 1 plus q, and there is x minus 1 over 1 plus q plus y squared plus z squared half. So analogous, in an analogous way, phi2, the second part, can be also expressed as a gm over a and a function of q and these reduced distances. And now, okay, this can go away. The third part of the potential, which is the phi 3, it's minus 1/2 omega squared x plus y squared is equal to, okay, omega squared is gm over a to the third. But if we express this in this dimensionless quantities, we'll have a squared x squared plus y squared. So this will be 1/2 gm over a squared x squared plus y squared. So each part of the potential can be expressed as a constant gm over a times a function of q and all the distances that are in the units of the semi-major axis. Yeah? So from that, you can infer that the Roche lobe radius in these units will be some function of q. Yeah? And sometimes during these types of lectures in the tutorial classes, I ask the students to take the potential, take their computers, and find the function XL of Q, because that's quite an interesting exercise in thinking in 3 dimensions and integrating a simple volume, and then appreciating that people have done this semi-analytically in the past without computers, and they came with excellent approximate formula that you see here. So in 1955, there is this formula by Koppel, then there is this formula by Paczynski, which is equivalent because it's just a redefinition of Q, whether it's M1 to M2 or M2 to M1. These two formulae are more recent, they're from '83, but nobody has been really finding or thinking of anything better since those times, and they work pretty well. So I think that you should appreciate that the Roche lobe volume is it's not a real sphere. It has a few symmetries, but it's not, for example, it's not rotationally symmetric along the axis that connects the two bodies. It has an up-down symmetry. It has the reflection symmetry, but this is not a very simple piece of space, and you have to solve these simple equations to get the proper shape of the Roche lobe volume. So this is an important result, and we'll use some of these functions XL of Q to investigate the properties of the Roche lobe and how the Roche lobe changes with during the mass transfers. Okay, so now these are the few examples of Roche lobe, of potential equipotential surfaces in the Roche lobe potential. The case A is when we have the system that is not filling the Roche lobe. There is a system that is overfilling its Roche lobe, and the two stars are having this common envelope around them. The common envelope is not the right word because it's reserved for something else. This is the case when a single star overfills its Roche lobe, so it transfers the mass, and the mass falls over through this saddle point and flows down to the second star. And of course, you can have systems where two cores of the stars are overfilled with they're overfilling the Roche lobe, and then you cannot really expand the Roche potential to the very high distances, because then you shed the mass very quickly, because the Roche lobe potential is falling down when you go away from the system. So in such a case, probably the rotation of there should be a binary here, is quicker than the rotation of the envelope, so that the fall down due to the centrifugal force is not that strong as in the classical Roche lobe potential. Now that we have the shape of the Roche lobe potential, we know that there is a function like that, and we have some approximations. Let's try to estimate when will a star fill its Roche lobe. Right? What are the conditions for filling the Roche lobe? So let's get rid of that. And that as well. So we know in a binary we have to have a binary has to satisfy this relation. So period is equal to 2 pi times gm r to the third, or a to the third over gm. Now we have shown here that the radius of the star, A2, radius of the star, in this A2, I mean, that the, okay, the A2 is equal to A times Q over 1 plus Q. Excuse me? Did I forgot 1/2 here. You're right. Okay. No. No. Okay. Now, the Roche lobe of the star that is filling its A to the third, that is A times XL of Q. Yeah. So when the star fills its Roche lobe, we can write that A is RR over XL of Q, and when the star fills its Roche lobe, the radius of the Roche lobe is equal to radius of the star. Yeah? So we can insert this formula, so we can express A as a function of the stellar radius, of the stellar radius to the third divided by Gn x Q to the third. Yeah, and 1/2, so that I don't remember, so don't forget. Now, M and M1, where did they go? Oh, okay. M and M1, the mass of the star, are connected by this, so we can express M as 1 plus Q over Q times M1, yeah? Okay, so we have 2 pi, and we have the following: R star cube over G n 1/2 x L to L of Q to minus 3/2, and then we have Q over 1 plus Q to 1/2. Yeah? But when I see a combination like this, M divided by R to the cube, I cannot resist by replacing it with density, because that's just an obvious thing. So I have to write 4 pi over 3 here, 4 pi over 3 here, and this makes me happy. So let me just put the final result somewhere. So we have now, okay, 2 pi over G to the 1/2. Then we have 3 over 4 pi rho star to 1/2 XL to minus 3/2, and then over 1 plus Q to half, and this is equal to 3p over g rho to 1/2 x q over 1 plus q to 1/2. Okay. So a star will fill its Roche lobe when its density reaches a certain value, yeah, times this factor. So let me look at this what this factor really is. I think I will include this at this moment, and I can get rid of that. So we have the factor x. Okay, so let's look what at the the approximations. Let's look at the simplest one. XL equals to 2 over 3 to 4 third, 1 plus q to minus 1 third. So XL to minus 3 halves. This is 2 over 3 halves, 1 plus q to 1/2. And we have then the factors q over 1 plus q to the 1/2. Yes, we have this will be approximately equal to 3p over g rho to 1/2, and then 2 over 3 to the 5 minus 3 halves q to the 1/2. So this is approximate, and this really weakly depends on q. So for a given star, the period when it reaches the fills the Roche lobe essentially can be determined by its density. Once its density becomes low enough, and it's a weak function of the mass ratio. It weakly depends on the mass ratio. Here I showed that within this approximation, this is q to the 1/2, but this will be even weaker when we take the exact, weaker dependence when we take the exact formula. So this is an important thing that for the case of determining when the star will fill its Roche lobe, we essentially take the mass ratio and look at the evolution of a star when it increases its radius, and check when its density is falling, its average density is falling below this critical value that we can find from here, and that will be the period of the system when when the system reaches the when the star fills its Roche lobe. So now we know more or less that stars can fill their Roche lobes. We know when it's going to happen. So think about the simplest case of what will happen to a system when a star fills its Roche lobe. What will happen to their orbit when you start transferring mass from one component to another. So in the simplest case, when we have a very clean mass transfer episode, how it's going to proceed. We'll have no mass loss from the system, and we'll just slowly drop mass from one component to another. Yeah. So the mass in the system will be conserved. And since the mass is not lost, and there is then the angular momentum in the system will also be conserved. So what does it mean for the evolution of the orbit? We know that we can use this equation here, A equals to so we know that mass is conserved, angular momentum is conserved, only M1 and M2 are just, you let M1 and M2 flow from one to another, and you can check what the value of the semi-major axis will be. So J squared equals to M squared and 2 squared over M G A, and A is equal to J squared over G M over M1 squared M2 squared. So if you see an equation like that, can you see right away what will happen when we say have a flow from M1 to M2, and what will happen to the orbit? Or is there any special point with for A? No, this is very symmetric with respect to M1 and M2, so it's obvious that there will be that the special case is when M1 is equal to M2. What value A will reach when M1 is equal to M2? Large value, small value? Can you do quick analysis? Smallest value, yeah. So when M1 is equal to M2 is equal to M2 is equal to M second, we'll have A minimum, which is J squared over J, 16, yeah, 16 over M to the third. And so if this is the minimum, then if we move away from this minimum, then A is going to increase. So if we transfer mass from a more massive to a less massive companion, what will happen to the orbit? So if we transfer mass from a more massive to a less massive companion, we are going along this line that's A of M towards the minimum. Yeah? So the system will contract. And vice versa, if we transfer mass from less massive to a more massive component, the system moves away from this minimum, so the orbit is going to expand. So what does it say about the stability, potential stability of mass transfer? When is it easier to make the mass transfer stable? If we transfer from more massive to less massive, or vice versa, from less massive to more massive? If you go from more massive to less massive, yeah, and suppose that the sizes of your stars are the same, then the system contracts, and if the system was overfilling, a star was overfilling its Roche lobe, it is overfilling it even more, because the radius of the star stays the same, but A is becoming smaller. So in order for such a mass transfer to be stable, you need to contract the star much faster than the orbit is shrinking. And in the opposite case, when you transfer the mass from a less massive to a more massive companion, then you expand the system, and you have to expand the radius of the donor so that it follows the fact that the Roche lobe is becoming larger and larger. In order to overfill it, it has to evolve somehow, or there must be a mechanism so that it keeps on overfilling the Roche lobe continuously. So this is shown here. This is my nice graph of this formula for the A as a function of Q, and you can see that for Q close to unity, if Q is between say 0.3 and 3, the changes of the orbits are quite slow, but once you go to much higher Qs or much lower Qs, the response of the orbits to the mass transfer, to changes of the mass ratio is quite strong, quite rapid. So when we'll have mass transfers with Q very far from unity, we can expect that the system will undergo some really violent, potentially violent episodes. And here comes another. This is the summary of this, that in the conservative mass transfer, the system tightens when mass flows from more massive components, while it expands when the donors is left massive component. This is generally, it's trivial to show it for the conservative mass transfer. For the non-conservative mass transfer, when we lose some mass from the system and when we lose some angular momentum from the system, this is in general also true. So for most cases, this is true unless we assume extreme values for the mass loss or for the angular momentum loss from the system. So this is what I have prepared for today, but I think that I can go a step further and start talking about the slide. So this is what we just said. Okay, in order to expand, to generalize the mass transfer mechanisms, we have to include some either mass loss mechanisms or angular momentum loss mechanisms from the system. And a mass loss from the system is relatively easy. So if the mass flows over the edge of the Roche potential, it is likely to be, and it has a velocity that is larger than the escape velocity from the system, and it is relatively easy to lose some mass. Now, for losing the angular momentum, there is a number of mechanisms that operate and that may be important. So one is the mass loss in the winds, and I have talked about the mass loss in the winds, and we know that mass loss in the winds will tend to shrink the systems. But in what I have said, I have assumed that the mass loss in the angular momentum carried away by the wind is the specific angular momentum of on the surface of the stars. It doesn't have to be true. The angular momentum carried by the winds can be much stronger, and this is the case of the so-called magnetic braking. So that means that if we have a system with magnetic fields, then one of the stars has some magnetic fields. It looks like a big apple, and there are winds flowing away. Then these winds, if they are tenuous, they will follow the magnetic field lines, and they will decouple from the system at a radius that is much larger than the orbital size of this star. This is like the decoupling radius. That means that they will correlate with the system to a much higher radius, and their angular momentum here will be determined by it's omega, this radius, the Alphen radius, squared. The specific angular momentum will be much larger. And because of that, for each gram of the matter that leaves the system will carry away much more angular momentum than the angular momentum that is stored if it was just, then this matter had when it stayed in the star. So magnetic braking is a very efficient way of removing angular momentum from a system and it can work if one or two stars have sufficiently strong magnetic fields. So it can work, for example, if this is a pulsar and this is a giant with a strong wind. This can also work in the case when we have magnetic white dwarfs and say main sequence star with some wind. So that's an efficient way of losing the angular momentum. Then, if we have slow outflow of matter from a system and it flows slowly through the Roche lobe potential, then this is going. The matter is going to the system until it reaches L2 Lagrangian point. So the effective specific angular momentum will be omega squared times L2, which is larger than the radius where the star was rotating. So we will also enhance the angular momentum loss by when the wind is slow and it is slowly removed from the system via by overflowing the Roche potential. Then we can parameterize all of these mechanisms by introducing a parameter that the specific angular momentum loss is some factor times J over M, and assuming that this parameter is something, we can calculate what will be the evolution of the system when we remove the angular momentum at some specific rate from the system. And of course, there is the gravitational waves mode for removing the angular momentum from the system. And with the gravitational waves, of course, you can tighten two neutron stars, but in terms of binary evolution, this is the last episode, and it's not as interesting because it doesn't really lead to long-lasting mass exchanges and nice mass transfer that change the structures of the stars. But this gravitational wave energy loss is important in the evolution of binary white dwarfs and bringing them together and maintaining their the mass transfer in binary white dwarfs. So there are these various mechanisms, and in general, we can have the non-conservative mass transfer where we parameterize. In general, if we have the loss of mass and loss of angular momentum from a system, we can parameterize it as follows by having the parameters that describe such a process. We can have beta, which is the measure of the mass non-conservation. So we have the transfer from one star to another, and we have, this is M1, M2, and the part of it flows away. And the part that flows away also carries away some specific angular momentum. So the fraction of the angular momentum that is removed from the system can be parameterized by alpha. And this is a very simple parameterization and very simple simple model of working on that. And we can, in this simple model, we can quite easily write a formula that shows the orbit evolution, because we have dj over j is equal to alpha dm over m, and dj over j has to satisfy this equation, so it has to be equal to dm1 over m1 plus dm2 m2 minus 1/2 dm over m plus 1/2 dA over A. So 2 alpha plus 1 dm over m minus 2 dm1 over m1 minus 2 dm2 over m2 is equal to dA over A. So we can integrate this and obtain the following formula, that A over A naught is equal to m over m naught to the power of alpha 1, and then we have m10 over m1 squared, m20 over m squared, yeah? And of course, the parameter beta sits in the fact that the changes of m1 and m2 are not independent but say in this case m2 dot is equal to minus beta m1 dot. So if m1 is m10 minus d m, then m2 is m20 plus beta d m, and m equals to m0 Yeah. So we have this. Okay, and of course this depends on the particular simple parametrization that we assume, and we assume that the amount of matter, angular momentum taken from the system can be parameterized like this. I will show you tomorrow that we can also parameterize it in a little bit different ways, and the way to parameterize the angular momentum loss is it's like many things in this thing. This is a matter of art and not an exact science, because you just have to feel and think how this operates in a particular astrophysical situation. So here we have this formula, and the question to you is, does it reduce to the conservative mass transfer when we have well, does it reduce to the case of the conservative mass transfer when we put the right parameters? Yeah. How did the conservative mass transfer look like? Remember? In the conservative mass transfer, total mass was constant. Yeah? So this would be unity. We don't care about alpha. So then we have A times m1 squared, m2 squared being constant, which is consistent. So this is not completely out of the blue. Okay, so I think I'll stop at this point, 1 minute ahead of schedule, and we'll continue with mass transfers tomorrow. Thank you.